Hey friends, my name is C and you're watching MakesItEasy, and welcome to a new video for A-level fundamentals. And today we have 1.5 for solving cubic and quartic equations for the rules and examples video. And let's get started with cubic and quartic graphs. But before we get into it, don't forget to leave a like, subscribe, and ring the notification bell so you don't miss out on any future videos. And we'll get started with cubic and quartic graphs. So as mentioned before in the previous videos, all complex roots come in complex conjugate pairs. For example, it will be a multiple of 2. So let's say it could be 2 minus I, and the other root has to be 2 plus I, and so on. And the same principle applies to polynomials of higher degrees, for example cubics, which is a power of 3, and quartics, which is a power of 4. And here we have some graphs for cubic graphs and the quartic graphs. So there are different variations for the different combinations of real roots and imaginary roots or complex roots. So let's look at cubic graphs first. So the first example is where there are 3 real roots. So as you can see here, the graph crosses the x-axis at 3 distinct points. So here, here, and here. They are all 3 distinct points. That means it has 3 real roots. And in the second example, it's basically 1 real root because it crosses it once, and 2 complex roots because it doesn't cross on any other. That means this right here must be a complex root or 2 complex roots. And the third example is 3 real roots, but 2 roots are repeated. Well, as you can see here, 1 root is here, and there's 1 repeating root here. And for quartic graphs or x to the power 4 graphs, like the power of 4 graphs, we have 3 different variations. So the first one is where there are 2 real roots and 2 complex roots. So as you can see here, the general shape of a quartic graph is like a W shape, like this, for a positive, and this for a negative, right? So as you can see here, it's like a negative graph. So there are 2 real roots, these 2 are real roots, and there are 2 complex roots on the top here. And for the second example, there are 4 real roots because the graph crosses the x-axis at 4 distinct points. 1, 2, 3, and 4. And these 2 are repeated roots. And for the last example, it will be 0 real roots and 4 complex roots, or basically 2 complex conjugate pairs, because these 2 are like 2 complex conjugate pairs. And this could occur as well if it's like this. And we'll look into polynomials now. So we'll look into roots for quadratic, cubic, and quartic equations. And we've looked into quadratic equations last video, so I'll just give you guys a recap. So if f of z is a polynomial with a real coefficient, and z1 is the root of f of z equals 0, that means the complex conjugate of z1 will also be a root for f of z equals 0. So here's some note for you. And sorry, this should be a type. This is a typo. Should be then. And now we have cubic equations. So cubic equations has 3 roots, and it's in this form az cubed plus bz squared plus zz plus d equals 0. And as mentioned, for a cubic equation with real coefficients, it could have 3 real roots or 1 real root plus 2 complex conjugates. And for quartic equations, it has 4 roots, and it's in the form az to the power 4 plus bz to the power 3 plus cz squared plus dz plus e equals 0. And for a quartic equation with real coefficients, it could have 4 real roots, 2 real roots, and 2 complex roots, or 4 complex roots. So here's an example to solve quartic equation, and it's a very lengthy one, so I'll just talk through it slowly. So given that 3 plus I is the root of the quartic equation 2z to the power 4 minus 3z cubed minus 339z squared plus 120z minus 50 equals 0, solve the equation completely. So just looking at the question, the quartic equation, you would know that it's a quartic equation, and it could have either 1 pair of complex conjugate numbers or 2 pairs. And since reading the question, we know that 3 plus I is a root. That means the other root must be 3 minus I, and that means because they are both complex conjugates. So what you can do first is that you can find the quadratic equation with roots 3 plus I and 3 minus I. So you could use this method to find the quadratic equation, or you can just use the method where I did in the past few videos, where it's like z squared minus alpha plus beta z plus alpha beta equals 0. So you can use either method. So however, if you expand the bracket, it will be z squared minus 6z plus 10. So that means that we know that this right here is a factor of the original equation, because we know that this quadratic equation is made out of roots that are factors of the original equation. And here we have the quadratic equation that we expanded, and we know that it has to be multiplied by another quadratic equation so that it gets to the form is this right here with the quartic equation. That means that from here we can use common sense or use basically like polynomial identity and compare the coefficients. So let's look at this here. So we know that to expand brackets, you basically have to multiply this and this and this plus this times this times this plus this times this times this, right? And there are some terms that can only be done once. What it means is that we have this 2z to the power 4 right here. So the only way to get z to the power 4 is where there are 2z squared multiplying together. That means the only way to get 2z4 is az squared times by z squared. Because there are no other ways to do it, because if you times this by this, you get z to the power 3, or so on. That means z squared times by az squared equals 2z to the power 4. That means using this, we know that a must be 2. Right here, a must be 2. Because if this were to be 2z squared, then z squared times 2z squared, z squared times 2z squared equals 2z to the power 4, which is true. And then we have the other term that we have that's inevitable, which is the last constant term right here, minus 50. The only way to get minus 50 is to get both the constant terms on the left multiplying together. So basically 10 times by c. So what we know is that 10c equals minus 50. Therefore, c has to be minus 5, right? So therefore, c equals minus 5. So now we have some more complicated terms, because we know that, let me just zoom in here. So we know that this equation on top becomes the bottom equation here, where z squared minus 6z plus 10 right here, and a equals 2, and c equals minus 5. And this equals the original equation. So from here, we can work out the value of b by comparing the coefficients of z cubed, z squared, or z. What I mean is that we can basically find, because we know that b is attached to a z, that means it could be present in any of the roots, either z cubed, or z squared, or z, right? Or these three. So we can just choose one of the roots, one of the coefficients to focus on. And let's say we choose minus 3z cubed, right? That means you have to find all the roots here, like just multiply all the possible roots to find the coefficient for z cubed. And that z cubed has to include bz in it. So let's just do an example. So let's say we want to focus on minus 3z cubed, right? The ways to do it is to multiply z squared plus z squared times bz. Then we get you bz squared, right? bz cubed, not bz squared, sorry. bz cubed. And there's another way to get z cubed, which is minus 6z times by 2z, right? So minus 6z times by 2z will get us minus 12z cubed. And let's look for other ways to do it, and you can't, right? That means you know that bz cubed minus 12z cubed equals minus 3z cubed. So what we can do is that we can basically just factorize the z cubed from both sides. So this will be equal to b minus 12 z cubed equals minus 3z cubed. Cancel them out, and then you're basically left with b minus 12 equals minus 3. That means you can just basically plus both sides by 12 to solve for b, and therefore b equals 12 minus 3, which is equal to 9. So therefore we know that a equals 2, b equals 9, and c equals minus 5. Let me just write it here. So b equals 9. So therefore we can just simplify it to get this bottom right here. Let me just zoom in. So we have the original equation, 2z to the power 4 blah 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 right here. It will equal to the z squared minus 2z plus 10, and then plus 2z squared plus 9z minus 5, or like plus minus 5. And then you can just solve the roots from there, because you can just solve individual quadratic equation by using the quadratic formula or your calculator. That means the root will be equal to z equals 12, z equals minus 5, z equals 3 plus I, and z equals 3 minus I. That means from this we know that this equation right here has 2 real roots and 2 complex roots. And here's an example for quadratic equation. So we have this equation right here. Given that 2 plus 3i equals 0, find all the roots of g of z equals 0. So we know that 2 plus 3i is a root. That means the complex conjugate, which is 2 minus 3i, must also be a root. And let's just set it as alpha and beta. That means you can find the quadratic equation with this, right? So alpha plus beta is equal to 4, and alpha times beta is equal to 2 squared plus 3 squared, which is equal to 13. That means we know that g of z is equal to this quadratic equation right here. We basically have z squared minus a of alpha plus beta, z plus alpha beta equals 0. So basically g of z is equal to z squared minus alpha plus beta is equal to minus 4z plus alpha beta is 13, so 13. And then we have just a general term, is z squared plus bz plus c equals 0. Oh sorry, not equals 0, but equals the original equation, which is z to the power 4 minus 2z cubed minus z squared plus 38z plus 130 equals 0. So we know this is true. That means you can find some terms first. So from this we know that z squared times by az squared is equal to 1z4. That means a must be 1. Right, so. And we can find c. c will be equal to 13 times c will be equal to 130. That means c equals 130 divided by 13, which is equal to 10. That means equal to 10. Oops, 10. Like so. That means we can rewrite the equation to get, let me just rewrite it here, to get z, oops, it's not working. Let me just rub it out. Which means that it's equal to z squared minus 4z plus 13 times by a is 1, so it's just z squared plus bz plus 10 equals the whole equation on the right, z to the power 4 minus 2z cubed minus z squared plus 38z plus 180, like so. That means we can just compare some terms, and I'm just going to use the z cubed term because we did it just now. So just going to focus on this. So we're going to find the z cubed coefficient on the right here. So to get z cubed, we can do z squared times by bz, which is bz cubed. And the second one will be minus 4z times by z squared, which is minus 4z cubed. And that will equal to the z cubed coefficient on the right, which is minus 2z cubed. Minus 2z cubed. Therefore, we can cancel to get b minus 4 equals minus 2. And therefore, b equals 2. That means we can just rewrite g, and g of x equals z, let me just write here, equals to z squared minus 4z plus 13 equals z squared plus b is 2, so plus 2z plus 10 equals 0. And from now we're just really close. We can just solve for z straight away. So this should be z, g of z, not g of x, because we have z as a variable. So g of z. That means we can just solve this by just doing g of 0, right? G of 0. And I'm just going to use my calculator to cheat because I'm lazy. So I'll just solve those two equations. And to solve these, you can actually just use the quadratic equation, or the formula. Quadratic formula. So the first one will be z equals 2 plus 3i and 2 minus 3i, because we know that that's what we're given in the question. And to solve the second part, which is this part right here, so the coefficient for a is 1, and b is 2, and c is 10, and that will get you another pair of complex conjugate pair, and that will get you, minus 1 plus 3i, and minus 1 minus 3i. And these are the answers. And we move on to the last part, which is basically square rooting a complex number. And although this is not in the textbook or in the Excel specification for the code here, it's an important thing to know how to do it. So we can use an algebraic method to find the square root of the complex number. So the question will be like finding the square root of the complex number 21 minus 20i. And I'll just talk through this. So we know that a square root of a positive number will be a positive number, and a negative number, and the square root of a negative number will be equal to the imaginary unit. But the square root of a complex number will always be a complex number. So we know that the square root of 21 minus 20i will be equal to a complex number. Let's just set it as p plus qi, or you can do a plus bi or x plus yi, doesn't matter. So therefore we can just set it as this right here. So we let p plus iq equals the root of the 21 minus 20i. And therefore we can just basically square both sides to get p plus iq squared equals 21 minus 20i from here. And we can basically just expand this and collect terms, and it will be p squared minus q squared for the real part, plus 2pq equals I equals the original expression right here, 21 minus 20i. Therefore, we can just group real parts and imaginary parts. So we know that p squared minus q squared equals 21. Therefore, it's right here. And we know that 2pq equals minus 20. That means it's right here. Or like pu equals minus 10 because I divided both sides by 2. So therefore, we can basically just solve for p and q, right? So we can rearrange the second equation right here to get q equals minus 10 over p, and we can substitute into the first equation. So p squared minus q squared, q is minus 10 over p, so it's minus 10 over p squared equals 21. And therefore we can just solve for p straight away by just basically rearranging and solve for terms. So you get p squared equals 25 and p squared equals minus 4. And solving that gets us p equals plus minus 5 and p equals plus minus 2i. And we can basically find the corresponding q value. So if p equals plus or minus 5, q will be equal to plus or minus 2i. Or if p is plus or minus 2i, q is plus or minus 5i. So now we can substitute the values into the p plus qi, and we can use either set of the answers because they both give the same answer. So therefore we will get plus minus 5 plus minus 2i, because you just use this p plus iq. Hence, the square root of 21 minus 20i equals plus minus 5 minus 2i. And it's important to note that the symbol inside the bracket is the same as the symbol of the original given sign. Right here, note the symbol for the imaginary part in the bracket will be the same as the one in the equation or the question. And that's the final answer for how you would solve the square root of a complex number. And that's it for this 1.5 for solving cubic and quartic equations for the rules and examples. And I hope you'll find me useful and helpful, and if you did, please leave a like and subscribe and ring the notification bell so that you don't miss out on any future videos. And if you have any questions or any constructive feedback about my channel or my YouTube or Instagram, you can leave down in the comment section and I'll reply to them. And check out my social media in the description, for example LinkedIn or YouTube or Instagram. And if you need any learning resources or any teaching resources, you can check my website in the description or you can type it out in your browser at www.makesiteasy.com. And I hope you'll find it useful and helpful, and I'll see you all in the next video, which will be 1.5 solving cubic and quartic equations for the questions video, which will be the last video for topic 1. And in 2 videos time, we will be moving on to chapter 2, which is argon diagram, which is interesting. But until then, stay safe and happy learning.